Hi everyone. So in this video, I'm going to be reviewing the fundamentals of formula writing. That's taking a compound's name and putting it into formulas. This is an absolutely essential skill we need in chemistry for the rest of the year. So you'll need your ions reference sheet, and it wouldn't hurt to have a periodic table handy just to keep it all in context. So the types of formulas that you need to know how to write are going to be ionic and covalent. You know it's covalent when it has these Greek prefixes, mono, di, tri, tetra, and so on. You know it's ionic when it doesn't. Just for some context here, we are not going to be doing what we call type 2 ionic compounds. That's any transition metals. So if you're watching this from a different class than mine or a different year than 2021, this will not include that type of name. All right, so let's start with the basics. Let's say we want to come up with the formula of an ion such as magnesium iodide. Okay, so it's not as simple as writing MgI. You can't just stick it together blindly. What we need to do is check the ions. Now, why ions? How do I know this is ionic and not covalent? Because I don't see a single Greek prefix, mono, di, tri, tetra. I don't see anything like that. So magnesium is Mg with a charge of 2+, right according to the sheet here. Find Mg 2+. Iodine is I-. And as you can see on the sheet, it's literally named magnesium iodide. Okay, so Mg has a charge of 2+, iodine has a charge of -, which is 1-. Now these need to balance in a way to cancel out the charges. So we're going to need 2 of these iodines to balance out the 1 magnesium. Magnesium comes first because positive always comes first. So it's going to end up being MgI2. And a quick way of looking at this is, I call it the crisscross rule. The number here will go after the element here. The number here, now keep in mind that number is a 1. It's going to go after this one here, but remember we don't write 1s. So it's like this number crisscrosses to the magnesium. This number crisscrosses to the iodine, MgI2. Let's say we want aluminum oxide. So aluminum is Al with a charge of 3+. Oxide is O with a charge of 2-. So we crisscross these, and we end up getting Al2O3. And just to kind of visualize this, sometimes it helps to really see it balanced out. Notice how if I have 2 Als and 3 oxides, you see how that's balanced? 3+, 3+, 2-, 2-, 2-. This is the ratio that aluminum oxide has to exist in. It cannot exist in any other way because it's not balanced in any other way. It's a 2-to-3 ratio, which we write as Al2O3, aluminum oxide. Let's mix in a couple polyatomics. Polyatomic ions are the ions you see on the reference sheet here. These are combinations of elements that stick together like a team. Atoms, I should say. Atoms of different elements that stick together as a team, and they have a charge. All right, so let's say we have, let's go with aluminum nitrate. Okay. So aluminum is Al with a charge of 3+. Nitrate is NO3 with a charge of -. Please note, it's not NO with a charge of 3-. That would look like this. But that does not exist. There is no such polyatomic ion. It's NO3 with a charge of -. So we're going to need, if you think about this in balancing terms, in order to balance out and cancel out the 3+, we would need 3 of these nitrates. See how this is now balanced because it's 1-, 2-, 3-. So my formula is going to have 1 aluminum and 3 nitrates. Anytime you have more than one of the polyatomic ion, you need parentheses around it. So in this case, Al parentheses NO3 close parentheses 3. That's the formula for aluminum nitrate. Please note, at no point are there ever charges in an ionic compound. Charges cancel out in ionic compounds. That's the whole point. no charges should be written. No charges here, no charges here, okay? If we see something like Mg2 plus I2 minus, that is wrong. There are no charges in ionic compounds. The other thing is there are no superscripts. Superscripts are these raised up numbers. Sometimes I see things like this. Or, well, usually it's not Mg2I. What I'll usually see is this. That is not correct. The 2 has to be a subscript down here. You know, just like H2O, that 2 has to be below. All right. Let's do another polyatomic. Let's say we have calcium sulfate. All right. So calcium is Ca with a charge of 2 plus. Sulfate is SO4 with a charge of 2 minus. So notice how it's already balanced. 2 plus, 2 minus. You're just going to put it together as CaSO4. No parentheses because there's only one sulfate. Now, if you use the crisscross method and you said Ca2, SO4 in parentheses 2, you need to simplify that down. Ionic compounds must be in their simplest form. You think of it like their empirical formula. It has to be the simplest one for any of these ionic compounds with crisscrossing charges. CaSO4, calcium sulfate. Let's do one more. Let's do ammonium, which is rare. Well, not rare. It's rare in the sense that it's the only positive polyatomic ion. So ammonium, and just to be clear, it's not the only one. It's the only one on our reference sheet. Let's go with ammonium sulfide. Ammonium is NH4 with a charge of plus. Sulfide, not to be confused with sulfate or sulfite. Sulfide is here. It's regular old S with a charge of 2 minus. So notice we're going to need 2 of these ammoniums and 1 sulfide, giving us the formula, parentheses, NH4, close parentheses 2S. Let's switch in some covalent now. Covalent. Ionic bonds are always either going to be metal bonded to non-metal or anything involving those polyatomic ions. Covalent is going to be non-metal bonded to non-metal. And the non-metals tend to be these negative elements over here, plus H, and C will show up as well. And some others, you might see silicon, germanium show up in ionic covalent compounds like that. So covalent molecules are named using those Greek prefixes, which makes them really easy to write the formulas for. I like to say every time you see Greek prefixes, breathe a sigh of relief because you don't have to even think about charges, crisscrossing. You're never going to think about parentheses, polyatomic ions, nothing like that. It's literally the answer is right in front of you. You just take the prefix and the element next to it and write that as the first part. Take the prefix and the element next to it, write that as the second part. Simple as that. All right, so let's say we have triphosphorus, Hexa Hydride. I recognize that I have Greek prefixes. I breathe a sigh of relief because I'm not going to have to think about charges. Triphosphorus means P3. Now, just to be clear, P, when it bonds ionically, has a charge of 3 minus. This is totally different, and I'm not going to think about this. This is not phosphorus as an ion. It's triphosphorus, which tells me I have 3 P's. Hexa Hydride. Hexa is 6. Hydride refers to hydrogen, not hydroxide. Hydroxide is OH minus. Hydroxide will never show up in a covalent compound because it's an ion. Ions don't show up here. So hexahydride means I have 6 H's. I'll write that as H6. That's literally it. The answer is right there in front of you. 3 phosphoruses, 6 hydrogens. And you do not simplify covalent compounds down. Remember, for ionic compounds, you have to show them in their simplest form. Covalent, you cannot simplify this down. Because if you did simplify it down to pH2, well, that would be a different molecule. That would be phosphorus dihydride, as opposed to this one, which is a different molecule, law of multiple proportions, triphosphorus hexahydride. All right, let's go with sulfur tetrabromide. All right, so I see a Greek prefix here, tetra, so I know that this is going to be covalent. So I breathe my sigh of relief. But notice sulfur doesn't have a prefix. That means there's one of them. If the first element is only one, it doesn't get mono. Like we don't say, there is one of them, but we don't say mono. You wouldn't say monosulfur tetrabromide. Just like for the famous molecule carbon dioxide, we don't say monocarbon dioxide. We just say carbon dioxide. So sulfur means I just have one S. Tetrabromide, 4 bromines, Br4. Let's say we have pentanitrogen monofluoride. Fluoride. By the way, as a disclaimer, most of these molecules I'm coming up with on the spot don't actually exist in real life. Like N and F would never bond in a 5-to-1 ratio like this, but we're just going through the naming practice. All right, I see penta, I see mono. I breathe a sigh of relief because I know it's going to be super easy, and the answer is right there in front of me. Pentanitrogen means 5 nitrogens, N5. Monofluoride means 1 fluoride. Now, we don't write ones, but we just write F. That's it. So remember, when it comes to 1 or mono, if the first element has 1, you don't write mono. Well, you wouldn't see mono. If the second one has 1, you would. So for example, if we have a compound like silicon monoxide, and silicon is a metalloid, but it does appear in covalent compounds as if it were a non-metal. So silicon means I just have 1 Si. Monoxide is the form of 1 oxygen. Okay, so I'm going to type up a few examples. You should pause the video, work through these examples, and then you can play the video, and I'll quickly go through each of them. It's going to be a mix of everything. All right, so let's say we have barium carbonate and aluminum chloride, ammonium phosphide, tricarbon octahydride, and silver acetate. Okay, so pause the video, write out these 5. Here we go. All right, so barium carbonate, I know that's going to be ionic because I don't see any Greek prefixes. So I'm going to write my ions, crisscross, and write it out. Barium is Ba with a 2+ charge. Carbonate is CO3 with a 2- charge. 2 + 2-, see how it's already balanced? BaCO3, no parentheses. Aluminum chloride, again, I don't see Greek prefixes, so it's going to be ionic. So aluminum is Al with a 3+ charge. Chloride is Cl with a -, charge. A 3-to-1 ratio here, so you crisscross the 3 and the 1. I'm going to need 1 aluminum and 3 chloride, Cl3. Ammonium phosphide. Ammonium is NH4 with a charge of plus. Phosphide, careful, that's not phosphate or phosphite. Phosphide is P with a charge of 3-. So we need to crisscross the 1 and the 3, which gives us parentheses, NH4,3P. Tricarbon octahydride. This is covalent, so I breathe a sigh of relief because the answer is right there in front of me. Tricarbon means C3. Octahydride means H8. Simple as that. This is an example of a hydrocarbon, where you'll see this as a combustion reaction. In fact, this one has a common name, propane. Silver acetate, Silver is Ag with a charge of plus. Acetate, C2H3O2 minus. Notice the 1-to-1 ratio is simply going to be AgC2H3O2. Okay, so if you need some more practice examples, there are plenty of them in your notes throughout Unit 6 and Unit 7. There are worksheets available on Schoology through Unit 6 and Unit 7. You could certainly ask your teacher or go to any extra help session. Good luck.